Good morning, everyone. My name is Muhammad Asif, and I am a research assistant at Jeju National University, working in Network Convergence Lab under the supervision of Professor Wang Chao-Song. Today, I will talk about how AI technologies, especially intent-based networking and Hackley framework, can be applied to research networks for end-to-end automation and optimization, especially in the context of A3 foresight projects, which was previously presented by Mr. Mariam in the previous event. So I'll look into that how we will go beyond like to include intent-based networking with it. So my main goal will be that in this presentation. So moving ahead, this is the outline for my today's presentation. First, I will briefly introduce the motivation and background of the work. Then I will explain the A3 foresight project, followed by the SDN fundamentals. And then I will talk about that why SDN alone is not enough. And after that, I will move toward the intent-based networking. And in intent-based networking, I will explain why LLM are important and discuss industries and standardization trends nowadays, and then finally I'll explain the Hackley framework and our experience, how we get it, and then I will conclude my presentation. So moving ahead, first I will go to the introduction and motivation. So modern research networks are becoming extremely complex due to AI workloads, big scientific data, and distributed supercomputer environments. So manual network configuration is no longer scalable. Researchers need automation, intelligent, and self-optimized networks that can adapt dynamically to application requirements. So this was the A3 foresight project previously presented by the Mariam. They basically connected the three countries to share their high performance computing research data. That is Korea, China, and Japan. So the A3 foresight project is driven by the idea of open science without boundaries, supported by advance in large-scale AI models and data-intensive research. The goal is to create an advanced research data sharing infrastructure across Korea, China, and Japan, enabling seamless collaboration among supercomputing centers. Like their main goal is to how they will share the research data among all these countries. So for Korea, they took the KoreaNet, which is a research environment for them, and then for Japan they use RCCS ranking, and it is by Osaka University, and then China NSCC. So these are the three different countries. They're like collaborating their big data through some HPC. So moving toward the SDN. So software-defined networking or SDN separates the control plane from the data plane. I will show you in the upcoming slides that how these will be separated and instead of configuring each device manually, which was previously done by the traditional networks, that in SDN have a centralized controller, manages the entire network programmatically and enabling more flexibility and automation. So you are seeing this from the left side. There is a traditional network showing, and on the right side there is a SDN network showing. So here, if you see that there are two layers. One is the SDN controller are here in modern network, and now here the physical network infrastructure is separated from that. So previously in traditional networks, control logic and is distributed and configured manually using CLI here. CLI command, and SDN intelligence is centralized in the SDN controller. And here in the modern, you can use the SDN controller and using the protocol OpenFlow. So SDN provide programmability, but programmability is not alone is an intelligence, but like it is moving one step ahead from traditional network to separate this whole traditional network from command line to some control plane and the infrastructure plane. Then I will talk that why SDN is not alone is enough, because SDN requires operator to specify low-level policies. It does not naturally understand high-level intents, although it is moving toward the programmability, but it does provide closed loop assurance as well. So this lead us to the intent-based networking, which I'm talking about, and my suggestions for the HPC, the collaboration among these three countries, while we'll be focused on this intent-based networking. So this was the foundation of the evaluation of the network, that from 1990s, like the static memory configuration will be done, will start, and then in 2010, the SDN programmability control mechanism is evolved. After that, in 2020, intent-based networking and AI reasoning and closed loop were came into being in 2020, and after that now in 2025 and onward, they are moving toward the some AI orchestration, autonomous network that like moving ahead and evolving day by day. So intent-based networking allows operator to express what they want, not how to configure it. Just the system automatically translates intent into policies, deploy them, and continuously verifies whether the intent is satisfied or not. So this was the background of the intent-based networking. That first, like what will be the network challenges? In network challenges, we have some dynamically changing world, like as you see from the figures. Then manual decision, which was like may lead to under or over resource utilization. Then the solution automation is also a big challenge for the network, that how we will done it. So that was a big challenge for that. So for this, we came into being to the intent-based networking, IBN. And IBN, like we have to perform a single touch requirement, like a minimum, like we can say, moving toward the intervention of the human. And then how like abstraction above semantics can be done. Semantics is basically knowing the intent of the user. Then the zero touch operation that is done through IBM, and after that, upon IBM, we will combining the ML, machine learning techniques that to tackle it. So machine learning enables semantic understanding, converting human readable goals and to enforceable network policies, which was not done previously through SDN. And this abstraction is critical for managing large scale heterogeneous networks. This was like, we can say, the brain of the system nowadays, moving like applying some AI techniques. Then at last, that how these intent-driven semantic policies are translated through some AI techniques, like in intent-based networking. Basically, the operator gives the intent in natural language, and then rest of the work is driven by the machine learning to translate those intent into semantics and then into low level policies. So intent-based networking, like have here overview that a closed loop work, like first the intent is captured, then it translates into policies, then next policies are executed. And finally, the system monitors the network and adjusts automatically if intent is validated or not. So it is a closed loop orchestration mechanism. This is the, according to IETF, this is a standard of IETF, RFC 9315. IBM consists of intent capture, like mechanism, then translate, execution, monitor, and assurance. And at last, like we have to deploy this through some infrastructure. So in SDN, we have two layers, like the control and the infrastructure, the physical layer. But here in intent-based networking, we are considering three layers: the operator view. From here, the operator will give the intent in some natural language, and then here the control layer, that it will control all of the path and policies and deploy the ML in it. And at last, those policies will be deployed through some infrastructure view, in the, like we can say, in physical network. So the thing is, why LLMs are needed in IBM? This is the main question everyone like can have in mind. So large language models act as a bridge between human intent and machine learning low level configuration. They are low flexibility in natural language interaction while maintaining structural policy driven control. So the user can speak in natural language and the machine translated into semantic through some ML techniques, and that is translated into YML policies, and then we will deploy those to the SDN controller. So for the SDN controllers, like we need the policies, so all of these things is done through LLM, like the user gives the intent and then it translates those into policies and then deploy through SDN. This was like some global standards bodies are converging toward AI native closed loop end-to-end automation. This alignment confirmed that AI-driven IBM is not just research, but a future industry direction. Like IETF is define the intent, models, and semantic policies translation. Then the HC enables AI native zero-touch service orchestration with cross-domain assurance, and ITUT establish autonomy levels and AI assistance assurance for adaptive networks. So these are the global standards bodies that now are converting the AI native technologies to for end-to-end automation. These were the recent industry development in AI-driven IBM, which is presented by Cisco. They basically work on the operational noise to reduce it through some applying some AI techniques, and they are claimed that up to 5%, 75% they like succeed like in the reduction of the noise and improve the troubleshooting efficiency. So based on our experience in research network environments, AI-driven automation significantly improves performance stability, resource utilization, and operational efficiency. So this was like our projects we previously did in our lab. The intent are receive the intent from the operator, then generate the policies according to that, applying some ML AI technologies on that, and then like it create those policies and deploy through some mechanism, and it will be it is between like Seoul, Penghu, Daejeon, Gwangju, like these all of the cities in Korea basically. It is a Korean project which we did previously in our lab. We applied AI technique along with the IBM, then how the path like reservation scenario can be done and sharing their resources. Then I'm going toward the HACTI framework. So HACTI is an AI-driven framework designed for closed loop traffic engineering in research networks. It continuously monitor, analyze, and optimize network behavior using AI models. So this was the flow of the HACTI framework, like it operates in a closed loop, monitoring network states, making AI-based decisions, enforcement. Sorry for interruption. So HACTI operational flow, it is like they are doing AI orchestration closed loop, like to monitor the network state, making AI-based decisions, and enforcing actions and validate the outcomes. So this aligns naturally with the IBM principles, which I presented previously. Like for the telemetry collection, they collected through personnel, which is put that on each router to like adjust that the latency and all of these things, and it will show through Prometheus, like the delay, loss, and utilization of the bandwidth and all these things. Then AI inferences, they in HACTI ML models predict congestion and optimal service segment routing paths. Then policy computation will be they did previously in their operational flow. In the upcoming slide, I will show their architecture, and then the enforcement of those policies, and at last they will provide the feedback. So this was the HACTI architecture overview. Like raw data is collected, and then the HACTI orchestration is done here, and at last the path computation engine, they put a path computation engine, and then they distribute their traffic through the routers. This was previously presented by Marian Kiran in the APAN. So this architecture integrates telemetry collection, AI-based decision models, and network controls to provide adaptive and scalable traffic engineering. So we propose integrated IBM-driven HACTI system within each participant countries. This enables autonomous, coordinated, and intelligent data transfer across international research networks. So that was our suggestions for the A3 foresight projects, in which like the intent-based network module will be on the top, and it will be deployed in each country, receive the operator intent like QoS, latency, bandwidth, and then translate that to some segment routing policies by LLM, and then we will give those policies to the head team. So the head team execute that AI-based segment routing path optimization using GNN and DRL. Like we can also suggest some STGNN, spatial temporal graph neural network, along with this GNN graph neural network. If the topology is going dynamic, so we will moving toward the like some STGNN type of scenarios. And then the segment routing using segment routing MPLS protocols, some type of segment routing protocols will be used there. And the domain will be like in each country administrative, its domain is like will be handled independently from with each country. So this was basically this slide demonstrates how IBM driven hacking enables closed loop segment routing based multi-domain orchestration across Korea, China, and Japan while preserving domain autonomy. So basically, this was our suggestion of IBM to be deployed in each country like Korea, China, and Japan, and there will be a central PCE which we call federated PCE node. It will not just the central node. It will basically just have the abstraction level to like preserve the security of the system as well. So IBM handles intent capture and semantic translation using LLMs, and then this will give those intent to the Hecate controller, and Hecate AI-driven decision making and like close optimization will be done, and then it will pass through to the other routers, like we can call it some different regions. Like previously I presented that we have done several projects. So one of the project like we connect different cities of Korea. So like there we can consider it in each city will be there are different cities like Daegu and Jeju, like we can say. So how it will be connected? So it will be connected through some internal gateway protocol. We can use it IS -IS or SPF. These are both two protocols, intermediate system protocol and open shortest path first protocol, which is used for the internal gateway protocol inside that. And in each country, there will be a border router, which will be placed on the side of each country, and they will coordinate through this federated PCE node. So federation like enables multi-country cooperation without centralization. So together this form an end-to-end AI native research network control plan, and that's basically it was our suggestions to like we will deploy the HECT along with the IBM for the HPC foresight projects. So in my conclusion, we say that to conclude, intent-based AI technologies allow researcher networks to become self-optimized and adaptive, and coordinate together with the AI foresight projects offer a unique real-world environment to validate AI-driven high-performance data sharing. Our next step is moving toward like zero-touch operation by integrating multiple AI technologies into live research networks. Thank you all from my side. If you have any questions.
Yes, thank you. Thank you, Asif. Anybody the question about that? I have a question. And currently you explained is those contents is just conceptual, the proof of concept. So the Korean and the research network is running the working network. So it's how the gap is deploy the real learning network. There is a safe or the something like that. Yeah.
Thank you for
yes.
Professor, previously we did Asia Connect project.
Yeah.
Like we connect Malaysia, like Korea or some other countries.
Yeah.
Through some intent-based networking as well.
Ah, yeah.
Yes. So like intent-based networking is not like just we can say a conceptual thing.
Yes. How many countries joined that test bed?
So,
okay. Okay.
In some different research papers I did that work. So like we are actually deploying that, and I'm responsible for the like that NLP part, that how the intent is translated and to policies and then like deployed to the network. So it is I present this in the conceptual way. I just give our idea that how like these countries will be connected. Like we put Haiti as represented by Mariam Karen, but alongside that, like for the network operator, administrator, we will make an ease just to give in the entire international language. And for that, the IBM is the main thing.
Okay, thank you. Thank you for giving your talk. And yep, we're gonna the next presentations. Dr. Kyu Kim from KIST of Koreanet, update of the wireless and the inter-data centers technology. Kyu Kim, are you there? Wait a second.
Hi.
Okay. Yes, whenever you're ready and you're gonna start. Okay, fine. You start.
Hello everyone.
Hello.
Hello, and
Good.
thank you for joining this presentation. I am Yu Kim of KIST, and I've been presenting in the APRP working group regarding wireless and data center communication technologies since before. Today, I'm going to introduce Lucio file transfer service to you. Now let's begin. At the last APRP sessions, I introduced you the index project of KIST as a data exchange node rather than an internet exchange node. Index is required to handle large-scale traffic between data centers, not public internet traffic. This is particularly crucial for research data, which can be very large and sensitive. We conducted various research to support the high-speed transmission of index inter-data center environment. At last APAN59, I briefly introduced TCP BBR. BBR is a congestion control algorithm developed by Google, designed as a modification of traditional TCP congestion control to better suit data center environments. I researched TCP BBR as one of the technical considerations for inter-data center transmission in the index environment. And at APAN60, I introduced IDMA technologies such as InfiniBand and Loki version 1 and 2 over inter-data center network environment. I also showed experimental results using IDMA between two sites that Creonet connects to utilize more than 98% of 10 gigabps network capacity. And today, I would like to go up the network layer and introduce research on high-speed transmission technology at the application level. It is called as Lucio FTS, and it is an open source distributed data management system. It is originally developed for the Atlas experiment at CERN, and Lucio has evolved into a community-driven project that manages vast amounts of data across heterogeneous global infrastructures. In this presentation, I will walk you through Lucio's core architecture and its scientific use cases. I'm not an expert in transmission applications, but I'm in the process of researching various technologies related to index, so I will be able to deal with the deep contents. This table seems to I think it is the most important to introduce Lucio. Solutions that were previously used to transfer large files at high speed include the famous grid FTP and FPS3 used by the existing CERN. It can be understood that Lucio is not a position to compete with or replace them, but to use them to provide more upgraded service. It is crucial to understand that Lucio is not a transport protocol. It is an orchestrator. Tools like Grid FTP or FTS3 act as the mover, the left side mover, and they handle the low-level reliability and moving bytes from point A to point B. In contrast, Lucio decides what to move and where. It operates on a declarative paradigm, ensuring high-level policies like ensure 3 copies exist on map, while delegating the actual physical transfer to tools like FTS3 via plugins. This is a picture I draw using Gemini. I used Gemini to briefly explain the architecture of Lucio. If you look at the Lucio document, it is expressed in 4 layers of architecture, but I drew it more simply for ease of understanding. Think of Lucio as the operating system for scientific data. It provides a global single namespace that unifies heterogeneous infrastructure. As shown in the diagram, Lucio sits between the user clients like the CLI, Python SDK, and WebUI, and the underlying storage hardware. Whether the data is on disk, tape, and high-performance computing centers or commercial clouds, Lucio abstracts these details, allowing users to interact with logical layer without worrying about the physical locations. These are 2 main techniques of Lucio. The core power of Lucio lies in declarative data management. Instead of manually copying files, users simply define the desired state. For example, a single command can request 3 copies of dataset X on tier 1 sites. The rule engine then ensures that system converges to this state. If a site fails or data is lost, Lucio automatically detects it and triggers transports from other sites to restore the requested redundancy. This is automated self-healing. To manage a global data lake, right side, Lucio unifies heterogeneous data centers into a configurable mesh. Administrators define costs and distances between Lucio storage elements. In this diagram, you can see how different sites like Sun, US Tier 1, and commercial clouds are connected with associated costs. Lucio uses this distance metrics to optimize routing, for example, by preferring local transports over expensive transoceanic links to improve efficiency. This picture was also drawn using Gemini. Lucio employs a modular microservice-based architecture to scale horizontality. The ecosystem consists of specialized daemons. There are some daemons in this picture. The judge daemon acts as a brain, evaluating rules and triggering actions. The conveyor handles logistics, submitting transfers to FTS3. The reaper is the garbage collector, deleting expired data to free up the space. And finally, Hermes acts as the messenger, notifying external systems about events. Each component can be scaled independently based on load. Then, this picture shows, it also uses Gemini. This picture shows the cross-site data sharing. The life cycle of the data sharing is shown in this picture. The first, a file is ingested and registered in Lucio. Second, a user applies a replication rule to place it at site B. Then, third, the evaluation engine detects the missing copy. Then, fourth, the transfer is executed via FTS3 using third-party copy. Fifth, upon completion, the catalog is updated. Finally, users can access the file transparently from the new location. This entire pipeline is automated. This is a use case that a prime example of Lucio's capacity is this square kilometer array, SKA or SCA. SCA is still under construction, so data is not yet being produced, but the first test operation, which they called first write, is expected to be 2027, and facing a data stream of 710 petabytes per year, which exceeds any single site capacity. So SCA adopted Lucio to power its regional center network named SICnet. Data ingested at telescopes in South Africa and Australia is automatically replicated to regional centers in Europe and Asia based on policy. This shows that the Lucio can be used in the variety of fields such as space observation, in addition to the first invented particle physics field. Today, I gave you the brief overview of our ongoing research on Lucio file transfer system within a short time. Going forward, as a part of the index project, I plan to continue exploring and presenting on topics related to large-scale research data transfer between data centers. Thank you for listening.
Thank you, Dr. Kim. Anybody question about that and in here or on the remote site? Okay, I have a question. What is the Lucio's is the biggest advantage over the other solutions?
I think other solutions are used to as solutions, existing solutions such as grid FTP. They are just file transfer. They service file transfer, but this one is the higher layer service. So yes, this users just defines some state, and the system, this Lucio system makes all the data is one user wanted state.
Okay. Okay. Thank you again to your presentation. Thank you.
Thank you.
Yep. The next presenter is from India. His name is Sudhansu Ozaha, and he is not in here. So we're going to change the next the presenter. The Kaneyama-san, are you there?
Okay, just a moment. Hi, just a moment. I'm sorry, just a moment.
Yes, I'm sorry for that. We
no,
need a
that's
little
okay.
bit adjust. Okay. Please let me know whenever you're ready.
Okay. Oh. It's a little problem.
Don't worry.
Okay. So hello. I'm sorry. Okay. Hello. Okay.
Okay. We can see.
Okay. So, what
And share your PPT file.
Yeah. Okay. This slideshow. And a mistake. Must. And okay. Okay.
Okay. That's
Okay.
fine. Yes. Okay. It's good.
Okay. Thank you very much. So Japan is very cold, but I think Bangladesh is very hot. So I want to go the Bangladesh, but okay. Okay. I'm Kaneyama, so a storage engineer in RCCS. So as mentioned at the APRP working group during the APAN60 in Hong Kong, so the third generation HPC shared storage system. So it is so now is in service. Today I would like to talk about the service started. So and the data migration to the third generation system from the second generation system, and our future challenges. Okay, just a moment. So okay, this is so HPCI overview. This is data project. Okay. Okay, so this is a HPCI overview. So so this is I presented the before. So and so APAN60 in Hong Kong. So it is a very shortly introduced. So it is a national project and the central HPC project in Japan. So call is HPCI, so high performance computing infrastructure. So HPCI manage the infrastructure for use and access to the supercomputer in Japan, and HPCI select project to use supercomputers. So HPCI project provides network storage system for sharing the research data between the supercomputers. So this network storage system called HPCI shared storage systems. So this is my task. So next is HPC shared storage overview. So of course, main purpose of HPC shared storage service is stored and sharing research data between supercomputer in Japan. In addition, so with the third generation system, so we are also considering collaboration contribution to the open science, such as the data publishing and sharing. So I want to sort of collaborate it and sharing knowledge with the AC project. Okay, this is the sort of AC project. So we and so collaborated to the Moon Sensei, Professor Moon. So currently, the HPC shared storage operated by the University of Tokyo and RCCS, and data replication is performed between the two sites, and so enable the disaster recovery. And here, so we have the two sites. One site is the RCCS and more University of Tokyo. So this system is updated from the 2025 to third generation systems. So updated resulted in increase in capacity and faster metadata access speed. So now, so the storage was provided, so 95 petabyte, very big capacity of logical capacity to researcher. And the HPCI shared the shared storage system is so GFAN file systems here. And this is network and parallel file system and the open source file systems. Okay, I'm sorry. So this photo is here is so Riken RCCS. So my institute, the RCCS installed so many systems. For example, so this is a supercomputer Fugaku, and so QC. This is a quantum computing, and so AI systems. So and researcher systems. So we have the many. We installed the many systems in RCCS. So I'm sorry. So large capacity of research data and large data is making at the RCCS. Of course, so the next flagship supercomputer, so next Fugaku model will be so installed in RCCS. Maybe so here is installed. So it enables high-speed data transfer across those systems to HPC shared storage. So this is the system configuration. So storage system is DDN 400 NVX2, and so we have to 10 units. And the storage system to deliver more than 30 gigabytes per sec, read and write, so I/O performance per system unit. So with the 10 units installed, so result, so total is over 300 gigabytes per sec, very fast speed, and 2.4 terabps, so aggregated throughput. So here is this is my storage systems photo. So this is one rack is one unit is in rack in one racks. So per 10 racks. Maybe here is the same. Okay. And so, however, so currently upper network here is 1.6 terabps, but so they are planned to include this to the 2.4, I'm sorry, 2.2 terabps in the future. I think maybe 2026 we are updated. So external connectivity to SciNet network here. So SciNet is a scientific network in Japan, so operated the NII Institute. So it's limited to the 800 gigabps. It is very large bandwidth. Therefore, RCCS operated many systems here, and the internal network is very strong. So many users will be performed at the high-speed access to HPC shared storage systems. And I think 2026 and in the future, so we are connected to new AI analyze systems. Here. So next, the GFAM file system overview. But this presented before the APAN59 or so 60 workshop. So we introduce this is a very shortly. So the GFAM file system is network file system and so open source software. So GFAM is developed Professor Tatebe in Tsukuba University. So GFAM needs to the three components. And first is so metadata server, so called to the GFMD. And second is file server, GFSD, and client software. So client can access GFAM to use the fuse mount, to which allows the use of standard POSIX command. However, if you need high-speed performance access, so when GFAM specific command are typically used. I'm sorry, okay. Yeah. And this is so main main section. So after the service, so run of the third generation storage system. So we are executed data migration from the second generation system to third generation systems. So the key point is that this migration was so performed without stopping the service. So user were not affected and the user can write and read the I/O to our storage service. So we use the GFAM replication function to automate the data migration process. So, okay, since the stored data were already replicated at the University of Tokyo and RCCS second generation system, University of Tokyo and RCCS second systems, and so all data stored on both systems. So we have the two replications, and as a result, so data were transferred from the both storage system in parallel. And so this is okay. And day two system and network limitation, the transfer bandwidth from the University of Tokyo was limited to the 200 gigabps. So while that from the second generation RCCs was limited to 800 gigabps. Here. This is limited. So for RCCS, also the internal network, so also to impose limitation. We don't expected to the list, so reach the maximum performance in practical day-to file server issue and high user load. So for stability reason, so the metadata server was located at the University of Tokyo here. So which also introduce additional latency for the metadata update during the write operation from the RCCS. So this is a plan. So before starting, so the data transfer we evaluated the expected migration speed. So from the simple test, so we found that the metadata access rather than transfer bandwidth could become the limiting factor. So this was because lower performance metadata server from the second generation system was connected. So all the metadata has connected before. So I'm sorry. So for service stability reasons, so we were not able to remove this backup connection, so second generation metadata. So even so, it could introduce a bottleneck in file creation performance. So since our migration schedule allows 40 days, so 40 days for the transfer, so we decided proceed with migration while accepting these potential limitations. So we estimate that the transferring more than the 300, I'm sorry, 35 petabyte of data and over 200 12 million files could be completed in about 2 weeks, even while connecting user service. So this is my plans. So this is a result summary. So the data migration was completed about 15 days. It proceeded largely planned. From the October 24 and November 8, 2025. The result is a total transfer time about 360 hours. During the migration, we observed the maximum transfer bandwidth of 200 gigabps from the University of Tokyo and RCCS. So SciNet, so it is scientific network in Japan, is very fast. So on average, the migration throughput was this one, 28 gigabytes per sec, so which and so around 163 files per second in terms of the file creation rate. So file creation was a little slower than expected. So my plan is 200 files per sec. So I think the main limit of transfer rate was metadata bottleneck and lower than expected read performance of the second generation RCCS systems. So the graph shows some period is here. So the throughput become low, very low. So those periods correspond to the time. Correspond to time. So when we intentionally pause the migration for check failure and handling and configuration update for migration. Oh, this is a more detailed summary. So the detailed migration results are summarized in this table, and that graph. So during the migration, we continue the data transfer while adjusting systems parameter. So we include the level of parallel levels parameter, but once exceeded about 1,000, the throughput is limited. So parallel on just 1,000 is only limited. Yeah. So we stopped including its parameter. Yeah. So the average file size was about 160 megabyte. So and we observed little slower transfer when many small files were involved, or so user read and write activity including. So even in those situations, so we are able to proceed it with migration without affecting user service. So the smooth progress on the migration was strongly supported by the stability and of the GFAM and SciNet. Okay, this is last section. So this is final section. So next challenge of my task. So I believe that the AI and the LLM integration is also necessary for monitoring systems. So there are many possible ways to collaborate with AI, but in the near terms, we are focusing on the two main areas. The first is enhancing the analyzing environment. So also to our monitoring system collected the large amount of the metric data. So currently, we don't have big data analyze layer. So analytics layers. So we plan to use the time series LLM to build an analyzing environment to the connected monitoring systems. So the second area is the automatic generation of the dashboard and the graph. So we are exploring the use of LLM to generation dashboards, so allowing the user to easily obtain the information they want. Okay, so this is the last slide, so I'm sorry. So I would like to shortly introduce the time series LLM. So as time series LLM is very important things, I think. So LLM training only the times and time information and metric data. So those models are very lightweight, so enough to run interface on only CPU, so without require the GPU. So this LLM use very, very light. So in many cases, simply providing a list of timestamp and the metric value allows the model to predict future metric. So by visualizing those output, we can easily generate the future graph. So this is time series LLM, and future challenge. Okay, so this is finished. So I'm sorry, we are over time. So this is summary. So I finished the presentation. Thank you very much for your attention. Thank you.
Thank you, Kanayama-san. It's very great, the presentations. Anybody question about that? Yeah. Go ahead.
Thank you for your nice presentation. You mentioned in time series about the time series LLM about LoRa, L-O-R-A. Why this specific model like you are mentioning here?
I'm sorry, more big volume, please. Big, I'm sorry, very please more volume. I'm sorry, just a moment. So I don't hearing.
Professor, I'm saying that you mentioned here like for fine tuning like this model, like for time series, you use LoRa, L-O-R-A.
Yeah.
Why this specific model like you mentioned?
Because LLM uses only electric data or so I'm sorry, so data center data. So and so sometimes so we need to the LoRa or added running to the via metrics. But so
Professor, because I work in this, for this, like in my mind, we have like some alternative like Tiny Bird, like some other model, because LoRa has a very, like we can say, complex model. There are a lot of layers inside that. So for like time series, I think time series, this is just my suggestion, that for time series, we just can consider a lightweight model, so the system will be more efficient and sensitive or sensitive.
Yes, he just mentioned to the LoRa is very complexity,
yeah.
complex. So yes, his thought is the suggestion is something different. Yeah.
But I think so. IBM said so me and one shot is very strong in this model. So IBM so Granite.
So complexity in the IBM and they have the stable technology to using the LoRa architecture. So I understand that.
Yeah. Thank you very much. I'm sorry.
Yes, the Kanayama-san is, I have a question. Sorry about that.
Yeah.
I
Sorry.
think it's yes, dark data seems to be the big obstacle, the transmission performance. So what is the average, the percentage of dark data in your file system or storage?
Yeah. Now it's 90%.
90.
90%. Very so dark data means so I think cold data. So
Cold data, yeah.
Similarly mean so only so don't access the 1 year's data. Yeah, that's 90% in now. So this is very big program, I think. So we need to and open science because so many using the I want to more using data, research data in the for the researchers.
Okay. Thank you. Yes, cold data and dark data, same things. Okay. Thank you again, the Kaneyama-san.
Thank you very much.
And Professor Asila, are you there?
Yes, Jung-hoon.
Yes, your next turn. Whenever you're ready and start.
Okay, I'll share my screen.
Okay.
So I'm waiting for Prof. Kaneyama to unshare.
Kaneyama-san, please release the shared.
Okay, thank you.
Okay.
I'm
thank
sorry.
you. Okay, that's fine. Let's go ahead, Asila.
Okay, so you can hear my voice clearly?
Okay, very clearly.
Okay, because it's quite noisy here. Okay, everyone, thank you, Jung-hoon, for the introduction. Good morning, everyone. My name is Nur Asila. I'm from Nisti Putra, Malaysia. Thank you for the invitations for this talk. So today I'm going to share about the update on HPC at our University Putra Malaysia. Okay, so this is our vision. So we planning, or we hope we can establish University Putra Malaysia as a national hub for high performance and data intensive computing to address national and global challenges. So in order, if we have this vision, we can advance Malaysia's scientific sovereignty, accelerates AI and emerging technology research, and foster a sustainable collaborative ecosystem. So we started a very humble HPC in 2012 with around 8 physical nodes and 96 core. So this is like more than 15 years, almost 15 years ago. So this HPC serve as a grid computing and also some data intensive computing research. And in 2015, we have another one more node. And this server basically serve more on the hands-on and training for undergraduates and postgraduate students, where they get familiar with the parallel computing programming. And then we have another node in 2018 with one GPU, Tesla Volta V100, although it was very small, but it's very useful to UPM research. Many PhD theses and master theses completed with this helps of a GPU server. And with this server, we get awareness on how to implement the AI, machine learning, training, and inferencing. So then we are so lucky to get a decent HPC with a 3 worker node and 1 head node from the Asia Connect and TNCC grant led by Jeong Hoon himself. So this is actually the server that being served to all UPM researcher, which it has been very useful for training for the AI research and also inferencing for data intensive computing. So until now, it has been like an interim HPC for us to prepare in order to have more larger resources. So thank you again for TUTIAN and Asia Connect for this grant. It's very really useful for the UPM researcher. Okay, so next, so we had these numbers of users is last year's, but we get increasing numbers quite rapidly. So now we have more than 150 users, and all of them are using for the AI, machine learning, and training, and also data intensive computing. So this is the faculty institute that most users come from. So we have this current software in our server, and we are using the modulars to manage all the versions. And also we have the Slurm scheduler also to manage the job submission. Okay, so we are so lucky. So that's why I said this APRP grant, the one that we have, is very good to create awareness and prepare our users in order to have kind of better resources or larger resources. So we managed to secure a grant, not a grant, budget from 13 Malaysia's plan. So it is around 2.2 million ringgit Malaysia, around 500,000 plus USD. So with this budget, we purchase 4 units CPU node, and this node in total we have around 1,024 core, and we have 1 GPU node with 4 NVIDIA H200. So the size of core is almost like 10 times of what we have right now. And for the GPU, we have for NVIDIA H200. So I think it is quite a decent numbers because it has the MIG. So it kind of a decent resources to our researcher. So this HPC might be ready in like 2 months from now is expected. So we hope that everything will goes well with the development, with the setting up and everything. So we have 2 units for head and login node and 2 units for scratch and storage node, user storage node. And we also planning to use the cluster management system and scheduling for Slurm, and also probably not Ubuntu but Linux for the OS, and the compiler, scientific and AI libraries as shown. And so for memory storage and interconnect, so we expected to have large memory node as and I showed in the previous slide, and also the NVMe as a diskette stretch storage and so on. So this is currently in progress. We are so not really nervous, but expecting that everything will go well with the setup, and we're expecting like next month we can conduct a training, because right now the contractor, I mean the has to fulfill the time limits by end of February to set up everything. Okay, so in terms of sustainability for this HPC, in terms of having the human and operational requirements, we are setting up a HPC units and request to have HPC admin permanently staff, so we can have a proper training and then proper managed by this admin. So right now, we don't really have a dedicated HPC admin. So the job or the task is actually being regulated by my team. So it's not really organized because we have more I mean permanent job that we have to complete. So next, this is all the research demands currently in our university. So most of the requests from the machine learning training. We have also the data intensive computing from bioinformatics, computational chemistry, engineering, agriculture. We have quite a long queue and also backlog, but we manage to solve that problems. So they don't really have much choices, but they have to wait. So we hope that with this HPC, we can enhance the skill and user readiness, so we can have more user empowerment. We will to deliver comprehensive support for researcher at every stage, and we can have enhancements on capability to strengthen HPC expertise through this the new HPC and collaborations, and talent growth and knowledge sharing, and also the ecosystem development of the new HPC. So actually, maybe I accidentally skip what I want to mention is there is a new that we know that there is an Asian Initiative HPC that we are looking forward, and we hope by this Asian HPC initiative that being collaborate with KISTI and Green Indonesia. So we hope this collaborative can also assist us in enhancements of capabilities and provide with more resources, adding what we have right now. We already have this website in order to organize, record, or a request from HPC users from our university. So we also organize several workshops and beginners workshop for this HPC usage and expected impact of the new HPC. So this is our current HPC requirements, as I mentioned earlier, on AI, current HPC requirements at UPM. So we hopefully for the strong focus on AI and ML, balanced CPU GPU architecture. So and then high-speed interconnects and NVMe storage for the IO intensive workloads. So this is the thing that I want to mention just now, Asian Shared HPC initiative, that we really looking forward. So what I heard that is going to get ready in this year June. So that's a very good news for everyone. I think. In terms of governance and sustainability, as I mentioned just now, that we are requesting a permanent staff in order to manage and have a long sustainability for our HPC. We will define clear roles and responsibility for system admin, advisors, and research, and all the team for this unit. So we can embark a new journey on this HPC for everyone, to have more human skills, and expected to have in our universities. So a strategic move for UPM. So HPC is no longer optional but a necessity. So right now I can see that when we mentions AI means indirectly we need HPC. So in Malaysia right now, AI research is being supported and by our government. Everywhere is AI. There are so much budget and grants being offered to universities and researchers from the governments, such as recently the governments from Ministry of Health opened for 15 million grants for LLM for medical health and to improve the medical health system management based on the LLM. And then the government also provide around 25 millions to 5 universities to enhance or improve the AI research. So it means when there is AI, there must be HPC, especially for the GPU. So right now I can see that this is very important to us. We hope in current time we can have more resources. So the initiative benefits from this HPC, we can boost UPM research excellence and global visibility, empower multidisciplinary collaborations and talent development, and support new strategic goals in digital transformations, AI, and scientific sovereignty. So with this collective commitment, we can position UPM as a national HPC hub and regional leader in computational science. Okay, so I think that's all from me, Jung Hoon. Thank you for your time, and yeah, thank you for your time.
Okay, thank you, Asila. We are not enough time to. The last presenter is me. Thank you again. And anybody questions? Okay, I want to skip the Q&A. Okay, Asila.
See ya.
Yeah, see you soon.
See you soon. Okay, bye.
Morning. This is the last presentation of the Session-1, the APRP Asia Pacific Research Platform. I will introduce the Asia Pacific Research Platform and our strategies and the future plans. In the thesis, my contents is what is the APAN, the APAC working, the last two, the APAN meetings summary, and then in the Korea-China Japan collaborate for project such as Northeast Asia areas. And the third thing is a Korea research platform the current status and the related work and the company. And so the rapidly through this my contents and the point to point. The first one is, as I mentioned in the beginning of our session, we started this since 2018 APRP working group initiative. And the meaning is deploy the research platform, the architecture or infrastructure to ASEA Pacific areas. And we have 2 times, and every the APAN meetings we had 2 sessions. And our objective is to promote the distributed and shared HPC ecosystem in the Asia Pacific area and engage the APAN members and the ASEAN countries. Finally, towards the setting of the Asia Pacific Research Platform and become a part of the global research platform. The global research platform is to cover the whole Earth. So the many countries I mentioned before, some of the very few of the advanced country, US or China, Korea, Japan, or some Australia, and the advanced countries, they have owned their supercomputer. And the supercomputing power and the GPU power became an indicator of the advanced country. All the other countries, they don't have enough IT infrastructure, even though international networking, right? But research platform is aimed to the high bandwidth distributed HPC system. So how can we make the distributed system to the gathering through the high bandwidth network, and how can using the make a big one thing for regular IT infrastructure areas, such like Southeast Asia, the West Asia, and in the middle of Asia. So I think it's very important the behavior or the activities for the growing up together. So our the 2 of the major the research the funding we got a funding 2 of the major. The one is the Asia Connect, the fixed core project by KNCC, and we collaborate with Pakistan and Malaysia, Korea, and Australia. And Australia and Korea is been donated the country, and Malaysia and Pakistan is a beneficiary country. We set up these machines and giving some technology and tutorials how to using how the combinations is to implement the IT infrastructure. The second thing is A3 site project, a collaboration with Korea, China, Japan. And those countries, as they have their own the big supercomputing centers, we wanted to federate China supercomputing center, Japan supercomputing, and Korea supercomputing center. So I wanted to just summary the last 2 the APAN meetings. The first one is the 59 the APRP sessions in Yokohama in Japan. We have 30 sessions, and 30 sessions is 12 presentations from the 8 countries. Why change it?
It's in, please stop sharing wisdom.
Oh, really?
Are you sharing in 2 times? Share by locally and share by via Zoom? Can you share in one?
Yeah, even you can reconnect.
You can share to me.
Sure.
No, so, yeah.
Because of the
It's
channel,
different.
because of the channel sharing, you have to keep it.
Can you please share?
This one.
Like this. Sorry about that. We don't have, okay. That's okay?
Yes.
Yes, the 59 says major topic is several and the particularly NIT experience in the gene edit and sequence research and then the research platform for agriculture and shared storage system. And this is the presenters their topic. And this is the summary of the pictures of their presentation environment. And the sixth is APRP working group and the sessions at Hong Kong last August. We have 3 sessions and 14 presentations from 6 countries. And the main topic is several. It's 2 of them is remarkable building HPC infrastructure for ASEAN countries. And then the new HPC construction project. And the detail, the program and the presenters and their topics. And this is the summary of their picture and something like that. Now I can tell you the A3 foresight project. This is the collaborated, the international collaborated project of Korea, China, Japan. And in case of China and the Guangzhou Supercomputing Center, Sun Yat-sen University. In case of Japan, the Riken Institute and Osaka University. The duration is the 5 years. Each country's budget is right there. And the PI is Yutong Lu from China, the Kanayama Hidetomo from Japan, and the Jungmin Onmi from Korea. And this is a summary of our project. It's a data sharing infrastructure across Northeast Asia supercomputing centers for science. I can tell you this in one sentence. This project is final goal is how to support open science. How to support open science in Northeast Asia areas using open infrastructure. And open infrastructure meaning is distributed HPC based on high bandwidth. The many countries they have their own small or medium size or the bigger size is their system or server or storage. They just running just a standalone. Just a standalone, the capability is not remarkable. In case of China, they have over 16 supercomputer centers. All over 16 supercomputer centers is running just a standalone. In case of US is they have over 30 or 40 supercomputing centers. Most of them is connected with over 100 gigabps research network. It means that they running on the federated neighbors supercomputing centers and distributed HPC environment. That is very important. Many scientists just want to do this bigger size computing power, but nobody can support to provide that. But the few advanced country is become to support those problems requested from research areas. So one of the first steps is to establish this northeast the ASEAN areas between Korea, China, Japan. And this is how to make the project strategies. It's 3 categories. One is infrastructure units. It depends on the China. And the second thing is the data transfer units. It depends on the KIST in Korea. And the third thing is to separate the 2 items is data compression and the metadata units depend on in Japan. As earlier the presentations is Kanayama Hidetomo-san is explain about the data compressor and the metadata, how to the delivery, how to the managing. And this is the first year's summary. The below pictures is the initiative, the workshops held at this 1 year or so ago in China. With discussions is how the collaborations, system levels, not human level. The system levels are how the collaborations. It means that how to make the federation technology, each countries. And then we had today's preliminary learning, the research. And our the a little bit document, and we are make the human infrastructure and the system infrastructure. This is first year is a small the result is first thing is data space management infrastructure comes from China, and the data sharing layer, the right side the upper picture, comes from Japan. The low side is application areas, and the last one is workflow tools with the auto attention metadata. All those pictures and the separated research topic is consist to the make our aims project. The second year project, the plan is such like that. Survey and the deployment elemental technologies. And finally, the first phase, within 3 years, we want to make the prototype this between 3 countries. And the second annual international workshop will be held at the KISTI, the February 2nd week at the KISTI, Daejeon. And maybe 10 institutes and universities is attend. And in case of Korea, Seoul National University, Jeju National University, Kumo University, and the Hannam University and the KEI, Korea Environment Institute. In case of China, and the Gwangju Supercom Center and the Sun Yat-sen University. In case of Japan, the Riken Institute and the University of Tokyo. The third topic is Korea Research Platform and activities. We started this 2015, and at the first stage of the NRP in US, we became a global partner of NRP and the PRP project. And then 2018, the reading of APAN, the APRP working group. That year's is initiative, APRP working groups in APAN. The since 2021 is expanding the 7 Korea National Research Institute in domestic infrastructure. We a little bit build up the collaboration with the Neighbors Institute, and 2022, and we got to fund the Asia Connect project, and 2024 we got the A34 site program project. The red blocks is the main goal is just one sentence. The Korea Research Platform's final goal is establish a high reliability and high speed transfer system without boundaries between participants. The below 2 pictures are the left side is our strategy, and the right side is the practical infrastructure given by the KISTI. The KISTI is the Korea National Representative Supercomputing Center and the R&D Research Network Center, and the third one is we are the data centers. And this is the related the project is the Asif Mohammed is first he introduced his research topics. Those topics and the contents are the related research drive the KRP, and the name is a joint AI-based networking for CJK. How can the high performance connectivities among the countries, and using the HICATE and something like that. And the second thing is the research, related research is the, how can I say, environment, the climate and weather and disaster. And we're gonna the analysis for this disaster depends on the weather changes. The first, the picture is the modeling on our research platform, how to the victims occurs when the strong rainfall, some special areas. The second thing is how can deploy the LLM models on our machine at STM. And the third thing is a high performance research platform for gene and the bioinformatics. For especially and the gene seizures research is very useful for using the distributed HPC system. And this is the optional introducing the project, ASEAN Korea HPC project. The name is KADIF, Korea ASEAN Digital Innovation, the flagship project. This is the representative file is to make the 3.5 petaflops HPC build in Indonesia. and using for sharing for ASEAN 10 countries. 10 countries committed, decided how to deploy, how to make the strategy, and how to the using a balance time and the CPU, the blah, blah, blah. And currently, I think it's the end of this years and the build-up is prototypes in Indonesia. And then early next years in the running in the beta environment. And the interconnect is 400 gigabit and the storage in the 3 petabyte. Maybe I think it's a very good chance to the using and high performance computing environment. But I'm not sure how can the getting the authority to using this system. Maybe someone says that belong to this ASEAN countries, they can access through their government to this system. And this is the layout and conclusion. And the describe this as a fourth areas is conclusion. But the red the color is the I want to focus in these presentations. In case of the APRP working group in APAN, I think it's a collaboration with the representative university and the education areas. Why I think the many the seniors and the middle juniors and the beginners, I categorized the 3 layers is junior, senior, junior, and beginner. Beginner means that the students or the postdoctoral include. The junior, the researcher is in the young researchers. Senior is older generation. But the strategy and the policy is decided comes from the senior. But currently, our beginner and the younger generation researchers, they comes from a different background. That is AI. The old researchers, they comes from just on the terminal, on the desktop. And their decision and their thought is not to match the younger generation and the younger researchers. So, senior the researchers, I think, should provide many chances to younger generation to running their thought. I think the following is the senior decision, maybe not to catch up with advanced countries' technology. So I think it's the research platforms is we can't separate the small set the computing powers to give to university students and the younger researchers. That is the big way to overcome the touchdown this next round. In case of the A34 site program project, discovering the young researchers, we're going to find this China, Korea, Japan, and the younger researchers. They have a big potential. Any other generations, better than any other generations, they have a big potential because their background is just AI. When they were born, the AI environment is already running different thought. The older generation cannot catch up their thought. We have just the property as the IT infrastructure and funding. I think all funding and the IT infrastructure and the property is going through the younger generation. This is my opinion. And finally, in the HPC over HPN and the KRP, and the focus on the education and the deploy small set areas in domestic in Korea. Thank you for listening. Yes, anybody question about that? Okay.
Oh, good morning. So I'm back from the Philippines.
Yeah.
I came from also a university there and outside Manila. So we've been actually trying to to build our own, HPC facility there, because most of our faculty and students are engaging most of the time research and also projects with their thesis, capstone, something like that. So we do also have those projects funded came from the government and other private sectors, but one of our problem there is we do actually have the resources. I mean, it's not too very large, but you can just simply handle very basic computing resources or computing capability. So we've been trying to search for somebody or maybe could help us that can even maybe build a larger ecosystem with our HPC resources, or maybe we could share with our computing capacity with other region or neighboring country. So I was wondering if we could also join with the network that you're being doing right now with Japan, with China also. So in terms of how can we collaborate or how can we connect our computing power, computing resources, that would be my further question also. So are there any opportunity or how could we do it in our university just to, of course, to connect with you there?
Yeah.
collaborate with you?
Yes. Obviously your question is very simple and clearly. My answer is not easy because the advanced country you mentioned, the Korea, China, Japan, is their government is very sensitive to share the supercomputing power. Very sensitive because the advanced countries indicate the supercomputing power. Yes, the sharing issues is not easy, but I can tell you that you can become or the public the purpose in case of the NRP in US project. You became of the branch node. It's very easy. The small server and make this a DTN. DTN meaning is a data transfer node. You are the set up the DTN and apply for the UC San Diego or the San Diego Supercomputing Center. We want one of the international branch node for your big project. And if they accept your the suggestion, and your node became this one of the branch node in ASEAN area, and they share their computer resource a little bit. And you adding your machine, adding, and they are sharing more and more. At that time is the computing infrastructure sharing is the first stage is very important. But the main important thing is the learning the technology. Yes, many people is concentrated to the backend solution, how to the building HPC, how to the running HPC. But I think those areas is they just need the essential engineers small set. But many people is concentrated to this learning how to running the AI model and how to the combination AI and the traditional model. And the next stage is finally the winner group is, I think, experience using AI model running on the HPC infrastructure. So I can send you the document or the more detailed explaining the site, and I can I send you email. Please let me know your email and something like that. Okay, that's a good question. Yes. Okay, I want to wrap up this session, and we take in the 15-minute break, and we start again is 11 o'clock, session 2. Thank you for coming. Yep.
Thank you.
I think it was very good presentation and good English.
Thank you so much.
Very remarkable.
Thank you. Thank you.
Yeah.
Great presentations, everyone. Thank you.
Oh, are you there?
Yeah, I've been watching.
Yes, are you still there? Are you a little bit ashamed? Are you okay, Andrew? You're the head.
Yep, all good. Sorry, I'm just running 3 meetings simultaneously, so you'll have my attention.
Okay. Yes, I could not imagine without you in APAN.